warm welcome to all my fellow learners as we embark upon our journey today. After some contemplation, I decided to start things off with gate mathematics as opposed to a core engineering subject owing to two strong reasons. A, the weightage of gate mathematics is around 13 to 15% in the gate exam, which is quite significant. And B, the portion of gate mathematics is roughly the same across various branches. So I thought it would be in a greater collective interest if I could start things with gate mathematics. My primary references will be Erwin Kreyszig and B.S. Grewal. And I will start off with calculus. So let's get going. Let us start our study of calculus with the preliminary notion of functions, which I expect most of you to be already familiar with, but just for the sake of completeness, let me just briefly recapitulate it for you. Functions. Why care for functions? Now, one of the key interests in calculus is to be able to measure the rate of change of a quantity which varies with one or more parameters. In order to answer this question in more generality, we first need to make formal the notion of a quantity which varies with something, and hence it becomes imperative to introduce the notion of functions. So let me define it for you. Definition. Let A and B be two sets. The function f from A to B is a law or correspondence which associates to every element in A a unique element in B. This condition unique is absolutely essential. So let me just underline it for you. The sets A and B can be perfectly general in nature. However, for our study, the sets A and B will be either the set of natural numbers or the set of real numbers or the set of complex numbers. A and B, both sets will be either the set of natural numbers n or the set of real numbers r, or the set of complex numbers C. So what we have said is the following. We have two sets A and B. To every element, say x in A, the function associates a unique element in the set B, which is denoted by the symbol f of x. F of x is said to be the image of x under f. The definition says that every element x will have a unique image f of x, which means that the following is not allowed. We cannot have an element, say x prime, which is getting mapped onto two different elements in the set B. This is not allowed. The sets A and B have special names. A is called the domain of the function f, and the set B is called the codomain of the function f. Another set of interest is that of the range of the function f. Range of f is defined as the set of all image points of f. So basically, range of f is equal to the set f of A, which is defined as f of x such that x belongs to the set A. The range of f is always a subset of the codomain B, but not necessarily always equal to it. So, range of f is a subset of B, but not necessarily equal to B. We will illustrate all this by means of some examples. Let us start with the simplest example. F is a function from R to R defined as follows. F of x is equal to 0, which means that every element in the set R is mapped onto a constant element in R, which is 0. F is said to be a constant function. There is nothing special about 0. F could have easily mapped every element in the set R to some other constant, say 1. Even in that case, f would have been said to be a constant function. The domain of f, which is the domain of f in this case, is the set R, and the codomain of f is also the set R, because the role of the set A and B are being played by the set R. However, if we care to know about the range of f, it does not turn out to be R. In fact, it is a singleton set, which in this case is equal to 0. So, range of f is equal to a singleton set, which is 0. This is a good example to appreciate the fact which I had just written, which is range of f is a subset of the codomain, but it is not necessarily always equal to it, as we can clearly see that the singleton 0 is a subset of the real number R. However, 0 is obviously not equal to the entire set R. Let us take another example. F from R to R, f of x equal to x. This is another very special kind of a function which maps every element of R to itself. This function f is called the identity function. In this case, domain of f is same as the codomain of f, which is equal to R, as it is obvious. Moreover, it so happens in this case that the range of f is also equal to its codomain. Moreover, range of f is equal to R, which is the codomain. Let me stop at this juncture and recapitulate what we have done so far. We have rigorously defined what a function is. We have carefully looked at three important sets associated with a function, namely the domain set, the codomain set, and the range of the function. We also looked at two of the simplest examples of functions, namely the constant function and the identity function, and commented on their domain, codomain, and range. In the coming parts of the lecture, we will continue to look at some more examples, the standard examples like polynomial functions, trigonometric functions, exponential functions, logarithmic functions, etc., all of which will be hopefully assumed that the viewer is already familiar with. Finally, we will look at some of the popular classifications of functions based on different parameters. Thank you.